Hi everybody, I hope this video finds you well. In today's video, we're going to be moving on into section 8.7 of your textbook and taking a look at an alternate approach for solving non-homogeneous constant coefficient differential equations. In the previous set of videos for 8.3, we saw an approach called the annihilator method, or the method of undetermined coefficients, that allowed us to look at some very specific situations for non-homogeneous constant coefficient differential equations. The key in that method, in the annihilator method, was that you could determine that annihilator. And to determine that annihilator, what you needed to do was to be able to find a differential operator that annihilated or removed the non-homogeneous component. That turned out to be pretty easy if that non-homogeneous component was something that was a linear combination of an exponential, a polynomial, a cosine or sine function, a product of an exponential and cosine or sine function. But that was about it, because those were the types of functions that we knew differential operators that could annihilate them. So we need an alternate approach for what happens if that non-homogeneous component doesn't have a clear or immediate annihilator. This alternate approach that we're going to learn is what's called the variation of parameters. What we're going to do in this video is sort of work through and discover how variation of parameters works in the second order situation. So we're not going to do it in general just yet. Then in the next video, which will be 8.7 part 2, we'll generalize what we do in this video to any nth order constant coefficient non-homogeneous differential equation. So everything in this video is going to relate to second order ones, because that'll sort of help us actually sort of motivate this discussion, and then we'll generalize things in the next video. So let's talk about how we're going to sort of begin this. So to start with, let's consider what case we're going to be in here. So we're going to be considering the second order case. So we have this differential equation, y double prime plus a1 y prime plus a2 equals f of x, with a1 and a2 being constants. So this is constant coefficient and it's non-homogeneous. Okay, now since it's constant coefficient, we certainly know how to solve the corresponding homogeneous equation. So let's suppose that the functions y1 and y2 form a basis for the solution space of the corresponding homogeneous equation. Obviously, we know that we only need two things to form a basis here because we have a second order. And remember that the order of the homogeneous differential equation for linear differential equations corresponds to the dimension of the solution space. So we know that two functions linearly independent will form a basis for the solution space of the corresponding homogeneous equation. So what we're going to do is we're going to look for that particular solution. Remember, to solve the non-homogeneous, the general solution to a non-homogeneous is a single particular solution plus a linear combination of the homogeneous solutions. So we're going to try to find a particular solution that is of this form: u1y1 plus u2y2, where u1 and u2 are not constants, but instead functions. And the logic behind this, as the sort of name would imply, is that we're going to let these u1 and u2 sort of vary as functions in such a way that makes sure that they satisfy this differential equation. We won't be able to do that if we restrict u1 and u2 to be constants, because then y sub p would just be a linear combination of y1 and y2, and that means y sub p would actually be a solution to the homogeneous equation. So constants won't work, but maybe functions will. So these u1 and u2 are actually going to be functions. Now, this is an idea. Let's think about how we would actually then determine this u1 and this u2. Obviously, the y1 and y2 we would find by solving the corresponding homogeneous. So the real question is how to determine u1 and u2. Well, it's got to somehow relate to this equation. So let's think a little bit about what the derivative and second derivative of this y sub p would look like. Well, if y sub p is going to be u1y1 plus u2y2, that means y sub p prime, we're going to have to use product rule here, it would be u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. Now, it's sort of tempting to go ahead and differentiate this again immediately and then throw all that into here and then come up with some sort of equation. But there's sort of two reasons why we might not want to do that right away. One, unless we sort of enjoy really, really messy expressions, taking another derivative of this would mean that we'd have to use a product rule, product rule, product rule, product rule. Sounds like we'd get like 8 terms there. Would be pretty messy. At a deeper level, immediately taking another derivative here is going to introduce things that are like u1 and u2 double prime. And if you think about that, that doesn't make things any better for us. Our original issue here is we're trying to solve a second-order differential equation, meaning an equation that involves the second derivative. If we take another derivative right now and get u1 double prime and u2 double prime, then we've got an equation that involves second derivatives, and we're really back to where we started. So we're not going to immediately differentiate this again. Instead, we're going to add another constraint. And our idea here is that we should probably be able to get away with another constraint, considering so far we've only put one constraint on our solution. We've said that y sub p should be equal to this format. That's sort of one constraint. But we should have enough flexibility, considering that we're allowing ourselves 2 different functions, to add another constraint. So the second constraint we're going to do is we're going to say that these pieces that involve the derivative of u1 and the derivative of u2, that those, when we sum them together, are actually 0. In other words, in the format of yp prime, they actually don't matter. So we're going to put an additional constraint. We're going to do this additional constraint here. And we're going to say that u1 prime y1 plus u2 prime y2 must be 0. In other words, this plus this needs to be 0. So we're going to add in that additional constraint. Now, right now, we don't know if that's going to make things unsolvable. Maybe by adding this additional constraint, there won't be any solutions. We'll see that there are, but we don't actually know that. So for right now, we're just sort of making a stab in the dark here and saying, let's put this additional constraint. Well, what that means is that we can then simplify with this additional constraint that yp prime would actually just look like this, right? Because the sum of these two things is 0, so, well, if they're both in there, we don't really need them. We can just say yp prime looks like that. Now we can go ahead and describe yp double prime. If we do this, we will need 2 product rules here, but it's not going to be too bad. It's going to be u1 prime, y1 prime, plus u1, y1 double prime, plus u2 prime, y2 prime, plus u2, y2 double prime. So there's an expression for y double prime. All right, so now we have an expression for yp, yp prime, and yp double prime. Let's put all of those into the equation that they're supposed to solve, which is the non-homogeneous equation. So yp is supposed to solve y double prime plus a1y prime plus a2y is supposed to be f of x. So let's throw all that stuff in there. Yp double prime is supposed to be that, so we can throw all that stuff in first. u1 prime, y1 prime, plus u1, y1 double prime, plus u2 prime, y2 prime, plus u2, y2 double prime. Then plus a1 times yp prime, which is this expression here. So u1, y1 prime, plus u2, y2 prime, plus a2 times y, which we're saying is y particular, it's just of this form here. So u1, y1 plus u2, y2. And all of that is supposed to equal f of x. Now, I want to do a little bit of sort of clever gathering here. And I'm going to use some colors to sort of help maybe make this a little bit more understandable. We're going to gather this piece here, this here, and this here together. So let's gather all those, and we'll look at that as u1, y1 double prime, plus a1, u1, y1 prime, plus a2, u2, y1. Okay, so we're just going to gather all those. Then I'm also going to do a similar gathering on these pieces. This, and this. So that looks like we'd get plus u2, y2 double prime, plus a1, u2, y2 prime, because of course this a1 would distribute here as well. And then finally plus a2, u2, y2. Okay, now, I have missed a couple terms. There's these guys here and here, so I'll just tack them on at the end here. Plus u1 prime y1 prime plus u2 prime y2 prime, and that's supposed to be equal to f of x. Okay, now I want to notice that everything in blue here, right, has, I made a small mistake. Sorry about that. Let's just go back. That guy should be a u1 there. Yep, because that's this guy right there. And everything here looks good. Okay, good. So everything here in blue has a u1, and everything here in red has a u2. So let's factor those out. So this would be u1, y1 double prime, plus a1, y1 prime, plus a2, y1. And then everything here has a u2, so let's factor that out. u2 prime plus a1, y2 prime plus a2, y2. And then we've got all this stuff here at the end, u1 prime, y1 prime plus u2 prime, y2 prime equals f of x. Now, here's the whole reason we did that. What is this right here? Well, this is y1 plugged into our differential equation. What do we know happens when we plug in y1 into our differential equation? Well, remember, y1 is an element of the solution space of the corresponding homogeneous equation, meaning that when we plug in y1 into this equation, we get 0. So this entire thing here is just going to be 0. So this is going to be 0. This right here, though, this is y2 plugged into our differential equation. y2 is an element of the basis of the homogeneous equation, meaning that when you plug in y2, you also get 0. So we get plus 0. And then this stuff down here is all that's left. So we get plus u1 prime, y1 prime, plus u2 prime, y2 prime equals f of x. So putting that all together, we get u1 prime, y1 prime, plus u2 prime, y2 prime equals f of x. All right, so what do we have then? Well, if we think about it, we have two equations now. We basically can see that we have our additional constraint up here. And again, maybe we'll give ourselves a nice color to sort of see this. We have this additional constraint that we used, right? We said that that has to be true, and we just figured out that if that is true, then this has to be true. So in other words, we have these two equations and these two unknown functions to solve. Notice also these have the big benefit that what's unknown in them? Well, it's the same unknown in each, right? It's u1 prime and u2 prime are the two unknowns in there. Now, of course, the unknowns we really want are u1 and u2, but if we can figure out u1 prime and u2 prime, then integration would allow us to figure out u1 and u2. So let's summarize this on another page here. So we've just found out to determine, we don't need that in green. Okay, so to determine u1, u2, need to solve the system. Well, what do we say? Well, we came up with that additional constraint, u1 prime y1 plus u2 prime y2 is supposed to be 0. So that guy was u1 prime y1 plus u2 prime y2 is supposed to be 0. And after plugging in, we saw that it also has to satisfy this equation, u1 prime y1 prime plus u2 prime y2 prime is supposed to be f of x. So u1 prime y1 prime plus u2 prime y2 prime equals f of x. Now, we made up that additional constraint, and it turned out that making up that additional constraint made things simplify a lot. But like we said, how do we know that by adding that additional constraint, we didn't make an unsolvable system? I mean, this is a nice looking system of equations, but how do we know it's solvable? Well, it's solvable if, again, if you think about u1 prime and u2 prime as your unknowns, as your variable, y1, y2, y1 prime, y2 prime are your sort of coefficients in this system. So this means the coefficient matrix here is the Wronskian of y1 and y2, because we've got y1, y2, and y1 prime, y2 prime. But remember, y1 and y2, they're supposed to form a basis. meaning that their Wronskian is always non-zero, meaning that this thing is always going to have a unique solution. So, since y1, y2 are linearly independent, the Wronskian of y1, y2 never equals 0. So, this system will always have a solution. So that tells us we're always able to go ahead and solve this thing. We'll solve it for u1 prime and u2 prime, and then we'll have to go ahead and integrate to actually find u1 and u2. So this tells us that even though we just made up that additional constraint, this thing right here, out of thin air, it won't cause the system to be unsolvable, meaning this approach, at least in theory, will always work. Now you might say, well, what do we mean by always in theory it'll work? Well, like I said, this system is going to help you determine u1 prime and u2 prime. To actually figure out u1 and u2, which is what you need to build that particular solution, you would need to integrate. And as we know, in theory, integrating is easy, but in terms of actually performing that integration, it can be quite challenging. So while this variation of parameters approach will always work in terms of saying that this is a way to get the solution, it might not be actually practical to use it because we might get stuck on the integration. But in terms of overall view, this approach will work. So let's go ahead and summarize what we just figured out here. So this is sort of a summary of the variation of parameters method for second order non-homogeneous constant coefficient equations. Like we said, in the next video, we'll extend this to the nth order, but right now we're just working on second order. So suppose we have this second order non-homogeneous constant coefficient equation. We're using the notation that y1 and y2 form a basis for the solution space of the corresponding homogeneous equation. Then a particular solution, which is what we need to find the general solution to the non-homogeneous, will have the form u1 y1 plus u2 y2, where u1 u2 satisfy the equations u1 prime y1 plus u2 prime y2 equals 0, and u1 prime y1 prime plus u2 prime y2 prime equals f of x. And we're not going to state it in this theorem, but what we just said in the previous slide with the discussion of the Wronskian, not only is this going to be the sort of the equations we need to solve, we're guaranteed that there will be solutions because of the linear independence of y1 and y2. So there we go. So what this variation of parameters method says is that to determine this y sub p, you just need to solve these two equations for u1 prime and u2 prime, and then integrate so that you can get u1 and u2, and then you can build your particular solution. Let's take a look at a couple examples of this. As we'll see when we do these examples, this is a computationally intensive approach. It is definitely not as clean as the annihilator method, but it does have a wider range of use because we don't need to have to know an annihilator for that f of x. But computationally, it is going to be pretty messy. So let's take a look at some examples here. So we're going to try to find the general solution to this constant coefficient non-homogeneous differential equation. Y double prime minus 2y prime plus y is equal to e to the x over x squared. If you think about this, that e to the x over x squared is really x to the minus 2 e to the x, and we do not have a way to annihilate that. We know that to annihilate e to the x, you would just use d minus 1, but unfortunately that x to the minus 2, there's no way that we can get factors of x minus 2 attached to e to the x. If it was x squared e to the x, we know we would just use d minus 1 3 times. But the negative exponent really sort of gums up the annihilator approach. So let's use our variation of parameters. Just like before, though, you've got to start with your homogeneous solutions. So we're going to start with the homogeneous solutions. We'll rewrite into operator notation, d squared minus 2d plus 1 of y is supposed to be 0. Little bit of factoring, looks like that's going to be d minus 1 squared of y equals 0, which looks like the roots here are going to be r equals 1 with multiplicity 2, which tells us that our homogeneous solutions are of the form c1 e to the x plus c2, and then since we have multiplicity 2, we'd have x e to the x. So the homogeneous solutions are things of that form. Now we're going to try our variation of parameters. Variation of parameters. So we're going to say y sub p is going to be of the form u1 y1 plus u2 y2. So in other words, we're saying it's going to be of the form u1 e to the x. Notice that when we say y1 and y2, we're saying a basis, so you might as well just pick c1 and c2 to be 1 to make things nice and easy, plus u2 x e to the x. So that's going to be what our particular solution looks like. What do we know about these u1 and u2? Where u1, u2 solve the equations y1, u1 prime plus y2, u2 prime equals 0, which in this case is going to be e to the x, u1 prime plus x e to the x, u2 prime equals 0. And the second equation, y1 prime, u1 prime plus y2 prime, u2 prime is supposed to be f of x, which in our case is going to be e to the x, u1 prime plus derivative of x e to the x is going to be e to the x plus x e to the x, u2 prime, equals our f of x, which is our non-homogeneous component, which I'm going to write as x to the minus 2 e to the x. So we need to solve this system for u1 and u2, and then we can go ahead and actually integrate for u1 and u2. Now, it might look a little weird, but we can go ahead and actually write this in a matrix form, in an augmented matrix form. So let's go ahead and take a look at what that would look like. The coefficients would be e to the x e to the x, and then augmented with 0. And then we'd have e to the x and e to the x plus x e to the x. And we'd have x to the minus 2 e to the x. Now, we haven't worked a lot where we have coefficients that are functions, but things operate pretty much the same. Let's go ahead and divide this first one by e to the x. We can actually also divide the other one by e to the x as well. So our first operations are going to be 1 over e to the x applied to r1 and 1 over e to the x applied to r2. And of course, that's safe to do because e to the x is never 0, so we're not having any risk of dividing by 0. So we'd have 1x and 0, and we'd have 1 and 1 plus x, and x to the minus 2. Okay, now we can use this to clear this out here. So we're going to take row 2 and replace it with row 2 minus row 1. So we'll have 1x and 0, and then 0, 1, and x to the minus 2. Okay, there we go. Doesn't look too bad there. Now we can actually solve this. This equation here tells us that u2 prime of x is supposed to be x to the minus 2. Then we can actually go ahead and determine that. We can actually go ahead and use the other one first. So let's just go ahead and do that. And then this equation tells us that u1 prime plus x u2 prime of x is supposed to be 0. But of course, this guy tells us that u2 prime is supposed to be x to the minus 2, so we can pop that in there. So u1 prime x plus x times x minus 2 is supposed to be 0. So that tells us that u1 prime plus x to the minus 1 is supposed to be 0. So u1 prime is supposed to be negative x to the minus 1. Okay, now, is that our u1 and u2? Unfortunately not. That's our u2 prime and our u1 prime. Now we need to go ahead and integrate. So let's move on to the next page to do that. So we just figured out that u2 prime is supposed to be x to the minus 2, and u1 prime is supposed to be minus x to the minus 1. I believe that's what we found here. Yep, there we go. Yep, this guy here and this guy here. Now we're ready to go ahead and integrate. So u2 of x is going to be the integral of x to the negative 2 dx. So u2 here, and I'm going to stop writing the function notation, looks like it should be negative x to the negative 1. Now, normally we'd stick on a plus c, but remember, we're just trying to find a single particular solution, so it's safe to drop the plus c here and just choose it with c equal to 0. So whenever you're doing the integration step here, you can just choose c to be equal to 0 and just take the first one that you get. Here, we'd get u1 is going to be the integral of negative x to the negative 1 dx, and that looks like u1 is going to be negative ln absolute value x. So, is that our particular solution? Again, not quite. That tells us that y sub p is supposed to be y1, excuse me, we usually write it this way, u1 y1 plus u2 y2. So, this tells us that this is supposed to be negative ln absolute value x times the y1. What was our y1? Well, our y1 here was e to the x. So we'd get negative ln x e to the x plus our u2, which was negative x to the negative 1, times our y2, which was x e to the x. So x e to the x. We could clean that up a little bit and get our particular solution here is negative ln absolute value x e to the x minus e to the x there, because this guy would cancel with that. So, is that our general solution? Nope, that's our particular solution. So now we can say our general solution is y equals any linear combination of these homogeneous ones. So c1 e to the x plus c2 x e to the x plus this particular solution, negative ln absolute value x e to the x minus e to the x. Now, interestingly enough, not necessary here, this is totally a fine way of saying the general solution. You can actually see that this negative e to the x here actually is unnecessary in this situation, because this negative e to the x could be combined into here, where we'd end up with c1 minus 1. But of course, redefining the constant, we could just call that a new c1 or a c3. So it turns out actually this component, not really necessary. But this negative ln absolute value x e to the x, absolutely essential as part of our general solution. But if you miss that this guy could be folded in here, that's all good. We can just say that this overall is our general solution. So there's our particular, there's the linear combination of the homogeneous, we're all good. So the interesting thing here, of course, is that if we look back to where we sort of started from, there was no way to find an annihilator for e to the x over x squared. So we had to rely on this variation of parameters approach. Notice also when we got to this crazy mess here, yes, right, we had to do these sort of weird operations on our matrix that involved multiplying or dividing by functions and things like that. But we knew from that discussion about the Wronskian that this was guaranteed to have a unique solution. So we knew that we were going to get something that where we actually got a unique solution here. Okay, let's go ahead then and take a look at another example. All right. So we're going to try to find the general solution to this constant coefficient non-homogeneous equation. So we've got y double prime plus 3y prime plus 2y equals e to the x plus 2 over 1 plus e to the x. So before we do anything, let's start with the homogeneous. So we're going to take a look in operator notation. D squared plus 3d plus 2 of y is supposed to be 0. So we can do a little factoring that we get d plus 1 and d plus 2 of y is supposed to be 0. And that means it looks like our roots here are going to be r equals negative 1 with multiplicity 1 and r equals negative 2 also with multiplicity 1. So that means our homogeneous are actually going to look like c1 e to the negative x plus c2 e to the negative 2x. So we've got our homogeneous. Okay, now let's think about our particular. Let's look at this non-homogeneous component though. Notice this e to the x is not a big trouble with our old method of the annihilator. But this 2 over 1 plus e to the x, that's something we don't have a clean annihilator for. So does this mean that we should use variation of parameters for the whole thing? Well, not really. What we can do is we can find a particular solution for this part and a particular solution for this part, and then sum those particular solutions together, and it'll give us our overall particular solution. In other words, this will be an example where we actually combine the method of the annihilator with the method of the variation of parameters. So we're going to combine annihilator method with variation of parameters. So we're going to find y sub p sub 1 for y double prime plus 3y prime plus 2y equals e to the x using annihilator, because we can, and if you can use the annihilator, it's always easier. And then we're going to find yp2 for y double prime plus 3y prime plus 2y equals the other component, which is 2 over 1 plus e to the x, using variation of parameters. Then that means that y sub p will be the sum of those particular solutions. So if you ever see a piece that can be annihilated, it's easier to use the annihilator method on that piece. So that's what we'll do for e to the x. Then we'll use variation of parameters on this, and then we'll put them together for our particular solution. So let's go ahead, give ourselves a little space here. Let's find y sub p1. So now we have the equation d squared plus 3d, well, we already have it factored, might as well just use it like that, d plus 1, d plus 2 of y is equal to e to the x. What's an annihilator for e to the x? Well, this is 1x, so d minus 1 should annihilate it. So let's apply d minus 1 on both sides, d minus 1, d plus 1, d plus 2 of y, d minus 1 of e to the x, well, derivative of e to the x is e to the x minus e to the x, yep, it's going to be 0, so there we go. So what does that mean that our sort of trial solution is going to look like? Well, it looks like it would be something like a1 e to the x plus a2 e to the negative x plus a3 e to the negative 2x. Do we need all these components? Well, if we look back up here, e to the negative x and e to the negative 2x are parts of our homogeneous, so we don't need those guys. So we know that our trial solution is really just going to be of this form. So we're just going to use y sub t equals a1 e to the x. So let's pop that in there then, right, into our original differential equation. Original differential equation, y double prime plus 3y prime plus 2y is supposed to be e to the x. So two derivatives of this guy is just going to actually yield the same thing. So a1 e to the x plus 3a1 e to the x plus 2a1 e to the x is supposed to be e to the x. Looks like that adds up to 6a1 e to the x is equal to e to the x, which looks like 6a1 is supposed to be 1. So a1 is supposed to be 1/6. So our first part of our particular solution is 1/6 e to the x. So if we take 1/6 e to the x and plug it into this differential equation, it'll give us the e to the x component. Now we'll find something in that when we plug it in gives us this. Combine those together will give us something that gives us this sum. So whenever you have a sum of different functions, you can use different approaches on each piece. All right, let's go ahead and try to find yp2. So now we want to find yp sub 2 using variation of parameters. Okay, so yp2 should be of the form u1 y1 plus u2 y2, which means it's going to be of the form u1, our y1 here is e to the negative x plus u2 e to the negative 2x. Again, I'm just getting those from looking at the homogeneous, treating c1 and c2 to be 1 and looking at those as basis elements, where u1, u2 solve, it's got to be y1, u1 prime plus y2, u2 prime equals 0, and y1 prime, u1 prime plus y2 prime, u2 prime equals f of x. That's the general expressions for variation of parameters. What does that look like in our case? Well, it looks like it's going to be e to the negative x, u1 prime, plus e to the negative 2x, u2 prime, equals 0. And then their derivative, negative e to the negative x, u1 prime, minus 2e to the negative 2x, u2 prime, equals our f of x. What is our f of x here? Well, it's not this entire thing. We've already dealt with this, so it's just going to be that 2 over 1 plus e to the x. So 2 over 1 plus e to the x. Again, messy to look at it like this, so I do prefer putting it in the matrix form. Your book goes through and discusses like using Cramer's rule, which is sort of a just a formula approach that works very nicely for 2x2s. You can use that if you are comfortable with it, but I still think that the matrix approach is the easiest way. So we have e to the negative x, e to the negative 2x, 0, and then we have negative e to the negative x, and negative 2e to the negative 2x, and 2 over 1 plus e to the x. So, some different things we could do here, but let's multiply each equation by e to the x, just to make things a little bit easier. So, e to the x r1 and e to the x r2. So that's going to give us 1 e to the negative x and 0, and then negative 1 down here, negative 2 e to the negative x, and 2 e to the x over 1 plus e to the x. Now, very easily, we can use this guy to clean this guy out down here. So let's go ahead and replace row 2 with row 2 plus row 1. So if we do that, we should get 1 e to the negative x, 0, 0. If we're adding this guy onto there, looks like we should get negative e to the negative x. And then looks like we have 2 e to the x over 1 plus e to the x. All right, so we can now go ahead and actually solve this. Bottom equation gives us that negative e to the negative x times u2 prime is supposed to be 2 e to the x over 1 plus e to the x. Well, we multiply both sides by, what, e to the x, negative e to the x here. So we get that u2 prime is supposed to be negative 2e to the 2x over 1 plus e to the x. There we go. So there's our u2 prime. Now, of course, we're going to have to integrate that, but we'll save that for a moment. Then, when we go on to the other equation, we get that u1 prime plus e to the negative x u2 prime is supposed to be 0. We just figured out that u2 prime is this, so this would give us that u1 prime plus e to the negative x times negative 2e to the 2x over 1 plus e to the x is supposed to be 0. We can multiply that in. It's going to make that an e to the x, and then bring it onto the other side. And looks like u1 prime is supposed to be 2e to the x over 1 plus e to the x. So there we go. We now have expressions for u1 prime and u2 prime. Now, again, remember, this part is always going to be doable. The next step where we actually need to integrate, that's more up for grabs, right? Because again, integration is something where we have some functions we know how to integrate, other functions we don't. But certainly, if we weren't interested in a closed form, we could just say u1 is the integral of this, and u2 is the integral of this, without actually finishing those integrals. But again, the main idea here is that we know that we can always find what u1 prime and u2 prime should be. Let's go ahead then and actually finish this up though. So we'll need ourselves another piece here. So we just figured out that u2 prime, let's write it in order, I guess. u1 prime is supposed to be, what do we get there? 2e to the x over 1 plus e to the x. Yep, and u2 prime of x is supposed to be negative 2e to the 2x over 1 plus e to the x. So it doesn't matter what order we want to integrate them in, but u1 is going to be the integral of 2e to the x over 1 plus e to the x dx. This is a little bit nastier, but we can do a substitution here. W equals 1 plus e to the x. dw is going to be e to the x dx. So it looks like u1 is the integral of 2 over w dw, which looks like u1 is going to be 2 ln, we won't need the absolute values here, so ln w, and looks like u1 should be 2 ln 1 plus e to the x. Okay. Over here, we'll do the same thing. u2 is supposed to be the integral negative 2e to the 2x over 1 plus e to the x dx. We'd probably like to sub this as well, so it might be useful to first think about this as negative 2 e to the x e to the x over 1 plus e to the x dx. Then we can let w be 1 plus e to the x again. dw be e to the x dx. Notice that that's going to eat up this. And we will have to make a note that w minus 1 is equal to e to the x. So we'll get that u2 is the integral of negative 2 times w minus 1 over w dw. If we simplify that, that looks like u2 is the integral of what? Negative 2. And then that's going to be plus 2 over w dw. So u2 is going to be negative 2w plus 2 ln w, which means u2 is going to be negative 2 times 1 plus e to the x plus 2 ln 1 plus e to the x. All right, so now we have our u1 and our u2. So let's go grab ourselves one more page here. Okay. This tells us, now we're just sort of in the home stretch here, that yp2 is supposed to be u1 y1 plus u2 y2. So yp2 here is u1, we just figured out, is 2 times ln 1 plus e to the x. So this is going to be 2 ln 1 plus e to the x. What's our y1? Well, track that back down somewhere here. Y1 was that e to the minus x. So we can put that. E to the minus x. Plus the u2 here, which is this horrendous mess. So minus 2. So we can just say minus 2 times 1 plus e to the x times ln 1 plus e to the x. And then y2, if we go back and hunt that down, was e to the negative 2x. So we can use that. E to the negative 2x. So there's our yp2. So this tells us that our y sub p, well, our y sub p1, which we found using the annihilator method. Notice again, annihilator method much quicker. 1/6 e to the x. So we'll use that. 1/6 e to the x plus this 2 ln 1 plus e to the x e to the minus x minus 2 1 plus e to the x ln 1 plus e to the x e to the negative 2x. And if that's our particular solution, then our general solution is y equals c1 e to the negative x plus c2 e to the negative 2x. And then, just to spare myself a little bit, we'll just grab this guy here. Let's do a better job of that. There we go. Copy that guy, paste that guy right there, make him a little bit smaller. And there we go. Right? Now we just slap a little plus sign in between there, and there we go. There's our general solution. Any linear combination of the homogeneous plus the particular solution from the first part plus the particular solution from the second part gives us our general solution overall. Are there some ways to maybe simplify this guy? Well, it looks like there might be, right? It looks like if we maybe clean this thing up a little bit, might be able to distribute and sort of simplify this a little bit. But overall, this is our general solution. In our next video, we'll be moving on and we'll be taking a look at how variation of parameters can be used for higher order. We'll sort of generalize that pretty easily. It's not too hard to sort of see how it applies to higher order. But as you guys can imagine, it's already very messy to apply variation of parameters for second order. So we won't do many examples of using variation of parameters for higher order ones just because it is such a messy computational approach. But we will generalize it, at least in theory, in our next video.